Hello students, today we're going to be talking about the sound wave and the resonance of sound. So first of all, when you talk about the sound waves, whenever we make sound, for example, when you hear me speaking through this little speaker right here, what's actually happening is that the sound is created through vibration of the source object, and the source object in this case is going to be a speaker or the headphone that you're using to listen to me talking. And the thing is, as the speaker vibrate, there would be a little diaphragm down there that would create the vibration of the air that would compress and would actually make the wave that travels to transfer the energy and transfer the information from the source based on the vibration. So this transfer would actually have two components. First is the frequency of the compression. So the frequency of the compression would actually depends on how fast the source is vibrating, and then as it travels out, the distance that it can travel per one loop of the compression period is going to be called lambda, which is the wavelength of the wave that's traveling. So once we know the frequency and the wavelength that's involved in this sort of energy transfer, and as you hear me speaking right now, you can hear that the frequency actually does change based on the source. For example, if I speak with very low voice, this is very low frequency. Oh, I can make really high voice. So that high-pitched voice you heard is a higher frequency. And again, when you go back here, you would be able to calculate the velocity based on the known frequency and the wavelength. So we know from the mechanics that if you have an object that travels at the distance s divided by the time it takes to travel, you get a velocity of the travel. So same thing here. So since lambda is the length per one wave crest, and basically f is how often the oscillation happens. So if you multiply the length it travels per one period versus the frequency at which it travels, so you would actually have the length divided by time. So you would actually have the velocity of the wave that you can calculate. So if you know the frequency and you know the wavelength of the wave that's traveling, you can calculate the velocity of the wave that's traveling. Furthermore, in air, you also have the knowledge that the velocity does depend on the temperature. So you know that velocity for a temperature T given in Celsius, you could actually use this equation to calculate. So it is known that at the standard pressure, you would know that at T equals 0 Celsius, you can actually have the velocity to be 331.5 meter per second, and based on that relation, for a good linear approximation, as you increase the temperature, you can get an increase in the velocity because the air would actually oscillate faster, and that allows the faster travel of the sound that is traveled through air. So if you know the temperature, you can actually calculate the velocity based on this equation. So there are two ways in this lab that you could calculate the velocity. One is multiplying the frequency with the lambda. The other is using the known temperature to calculate velocity. So in this case, we'll use resonance to calculate velocity and compare it with the theoretical value that you could actually obtain from this second equation once you know the temperature. So in the lab setup, since you know that the theoretical value was going to be this much, so once you get into the lab, you go ahead and read the temperature in Celsius, plug it into this equation. This is going to be your theoretical value. And then in the lab, you're going to have a pipe that can actually be moved up and down, and you're going to have a pitchfork to hit the wave to go inside here. So the thing is, if the length of the free space in in this pipe is equal to lambda divided by 4, you create what you call the resonance. So the resonance is since this side of the pipe is open, and so it allows the vibration to oscillate nicely. But then again, since right here is actually the surface of the water, it actually does not allow a proper vibration here. So this is going to be called the antinode, and this is going to be called a node. So if you adjust the length such that it matches 1/4 of the lambda, you create what you call the resonance. So the wave that comes in does not have any sort of phase loss or energy loss, and it's directly reflected back. And this causes a constructive interference, allowing to hear really loud noise. So by adjusting this length to hear the loud noise, you could actually track down the first resonance and the second resonance. In fact, you could actually create the third resonance. So to create the resonance, the condition is that the top of the pipe has to be the antinode, and the bottom of the pipe that's actually sealed by water is going to have to be a node. So it does not allow any vibration. So the first mode is like this. Second mode is you add another half of the lambda. So one loop is half a lambda, because one lambda is one full wavelength, right? Like what I'm drawing here. And the next loop is going to be another half lambda. So in this lab, we're not going to try to find the 5/4 of the the 5/4 of the lambda. 5/4, sorry, 5/4 of the lambda. Regardless, you're going to be adjusting the length of the tube so that it matches 1/4 lambda, and you're going to be trying to find the second length, which is 3/4 of the lambda. So right there, you measure the distance between the pipe top to the pipe bottom. By bottom, I mean the water level, which you can adjust by adjusting the level of this guy. So the lower this guy is going to be, the lower water level is going to be. So you're going to have this little pipe here that you can adjust it up and down, and you're going to be constantly hitting the pitchfork or the tuning fork such that it creates the vibration go into here and make the proper interference. So the first time that you hear loud noise, record L1, and then the second time you hear the loud noise, record L2. So since you know that the vibration is given by the pitchfork, and the pitchfork is going to have a given frequency, so you can read the frequency based on whatever number is written on the pitchfork, so you know the F. Then you can calculate lambda based on L1 and L2. So L1 is going to be 1/4 of the lambda, and L2 is going to be 3/4 of the lambda. So L2 is going to be a little harder to find than L1, but you know that since L2 is 3/4 lambda, you can actually see if once you found L1, L2 should be 3 times L1. And you can calculate V from V equals F lambda, because F you can calculate from you can actually obtain it from the pitchfork, the number that's written on the pitchfork, and then you can calculate lambda from L1 and L2 based on this diagram here. So from there you can calculate velocity and then compare it with the theoretical value that you have based on the reading on the temperature. Okay, so as you do this lab, you want to start from a really high water level, and then keep hitting the pitchfork and lower the water level until you hear the first resonance and then the second resonance, and then you repeat this experiment by increasing the water level back up to the top and then all the way down again. All right, so then once you're done with the first repetition, what you want to do is you want to change the pitchfork. You're going to be given a series of pitchforks. So as you change the pitchfork, you can use the known velocity to find the frequency of the pitchfork by using V equals F lambda, because since you know V from the first experiment, and then you change the second pitchfork that you don't know F, but you know lambda from varying L, you could actually calculate F. So there are two parts of the lab. First, find the V. Second, find the F of the second pitchfork. Okay. All right. So here's the experiment that you're gonna have. So this is the water pipe that we've been talking about. By adjusting this guy, you can actually measure the length of the water level that you could actually hear the loudest noise. So the pitchfork, the way you use it, be sure to tie the bottom string onto your hand because you don't want to drop it, and then keep hitting it using this rubber hammer on top of the pipe here until you hear the loud noise as you adjust this guy up and down. Record L1 based on the reading on this ruler here. By ruler I mean a meter stick. Okay. All right, that would be all. So enjoy the lab. Thank you.